Though the cosine of a sum or difference identity formulas are very similar to the sine of a sum or difference identity formulas, tangent is uniquely distinct. However, tangent will be dependent on those previous identities that we've learned. Let's look at the tangent of a sum identity. Tangent of alpha plus beta can be expanded as tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. So in the top we have the sum of two tangents. In the bottom we have 1 minus the product of those two tangents. Notice how the tangent of a difference identity is very similar. Tangent of alpha minus beta can be expanded as tangent of alpha minus tangent of beta divided by 1 plus the product of those two tangents. That's tangent of alpha times tangent of beta. Now, it's always a good idea to compare and contrast formulas so that you can learn them well and come up with strategies for remembering them. So let me point out, if we have a sum of two angles in a tangent, the sign on the top will match the sign in the argument. Then I'm going to have the opposite sign down here in the denominator. This is true for tangent of a difference as well. If we have a minus here, we'll have a minus in the numerator and then the opposite sign in the bottom. Then the overall patterns of these two formulas are the same. We have the sum of two tangents in the top and 1 minus the product of those two tangents in the bottom. Let's see where the tangent of a sum identity comes from. We're going to build this formula on formulas that we have previously established. So we'll begin by taking tangent of alpha plus beta and expanding it as the ratio of sine of alpha plus beta over cosine of alpha plus beta. Then you can see we have the opportunity to use our sine and cosine of a sum identity formulas. In the top, we can expand sine of alpha plus beta as sine of alpha cosine of beta, and remember, for the sine formula we keep the same sign in between our terms, cosine of alpha sine of beta. In the denominator we have cosine of alpha plus beta, so the pattern for that expansion is cosine alpha cosine beta, and recall, for a cosine formula we change the sign in between and continue our pattern, sine alpha sine beta. Now our goal is to end up with this expression. So notice I can transform this first term into tangent of alpha by dividing that term by cosine of alpha times cosine of beta. Now, whatever I do to that first term, I'm going to have to do to all four of those terms in that expression. So we're going to build up quite a complex fraction here. I'm going to start with my first term, sine of alpha cosine of beta, and then I'm going to divide by cosine of alpha times cosine of beta. And I'm going to do that for the other three terms as well. So this one will be cosine of alpha sine of beta divided by the same thing, cosine of alpha cosine of beta. Well, that takes care of the numerator. Now I'm going to draw my main fraction bar a little longer just to keep my perspective here. Then I'm going to take the first term of the denominator, cosine alpha cosine beta, and divide it by the same factor. That is cosine alpha cosine beta. We got one more term to go. That is sine of alpha sine of beta, and it's going to receive the same denominator, cosine of alpha cosine of beta. Now the fun part, we get to clean house. For each fraction, we've got some common factors to cancel. Cosine of beta in the first term, cosine of alpha in the second, cosine of alpha and cosine of beta in the first term of the denominator, and the last one, no cancellation. Let's observe what remains. Out of our first fraction, we have sine of alpha over cosine of alpha. That is the definition of tangent of alpha. For our second factor, we have sine of beta over cosine of beta. We can recognize that as tangent of beta. In this term, everything canceled. That must leave behind a 1. And for our final term, we have sine of alpha over cosine of alpha, which is tangent of alpha, times sine of beta over cosine of beta, and that is tangent of beta. So we did the hard work to verify our first identity. Now, once that one's verified, the second one is a little bit easier to verify. Instead of using all the sines and cosines, we can simply express tangent of alpha minus beta as tangent of alpha plus negative beta. Then we have written our tangent of a difference in terms of tangent of a sum. And that's good news because we've already verified the tangent of a sum formula. So let's go ahead and expand this according to our tangent of a sum formula. We're going to take tangent of the first angle. Now remember, when this is a plus, we're going to have a plus in between our two terms in the numerator. And then tangent of the second angle, which we've expressed as negative beta. In the denominator, we're going to have 1 minus, remember we switched the sign for the denominator, and then the product of those two tangents. Tangent of alpha times tangent of negative beta. Recall, tangent is an odd function, so tangent of negative beta is equivalent to negative tangent of beta. If I apply that same identity to this term in the denominator, we're going to be able to extract a coefficient of -1. Moving that to the left here, it's going to switch that sign. Negative, or if we're subtracting a negative, we are simply adding. So we have 1 plus tangent alpha tangent of beta. Much easier to verify that identity. Let's practice using these formulas to evaluate the tangent of a non-common angle on the unit circle, such as tangent of 7 pi over 12, for example. Now, we've worked with 7 pi over 12 before. We learned that we can express that as pi over 3 plus pi over 4. Just want to show you the calculation out here in the margin, in case you don't remember where that came from. We're going to get a common denominator of 12 and adjust our numerators appropriately. So you can see pi over 3 plus pi over 4 is 7 pi over 12. So we can rewrite tangent of 7 pi over 12 as tangent of pi over 3 plus pi over 4. So we have tangent of a sum, and pi over 3 and pi over 4 are common angles on the unit circle. Expanding this with our new formula, we're going to find tangent of the first angle, pi over 3, plus tangent of the second angle, pi over 4. And we're going to divide by 1 minus, remember you changed the sign in the denominator, the product of those two tangents. Tangent of pi over 3, tangent of pi over 4. Tangent of pi over 3, that's 60 degrees on our unit circle. Recall tangent of 60 degrees or tangent of pi over 3. We're thinking of the y-coordinate divided by the x-coordinate. That would yield square root of 3. Tangent of pi over 4, that one's a piece of cake. That's 1. And then in the denominator, we're going to have 1 minus the product of those two. So 1 minus the square root of 3 times 1, which we don't necessarily have to write. So we do have an exact calculation, but let's go ahead and rationalize the denominator. Recall that to rationalize the denominator that has two terms, we're going to apply the conjugate of that denominator to both the numerator and the denominator. So the conjugate has the same two terms with a different sign in between. This is going to effectively cancel the radical from the denominator. Let's start with the denominator so you can see how this happens. If I go ahead and FOIL, we have the product of our first two terms is 1. The outside and inside terms are going to cancel because they have opposite signs. And the product of negative square root of 3 times positive square root of 3 gives me negative 3. So notice our denominator has been made rational. In the numerator, when we carry out our FOIL, we would obtain square root of 3 for our first two terms. Outside terms would give us 3. Inside terms would give us 1. And last would give us square root of 3. So when we simplify In the numerator, we would have 2 square root of 3 plus 4. Simplifying our denominator, we have negative 2. Now let's be really careful here. We want to divide each term uniformly by negative 2. So I'm going to go ahead and just split up the fraction. 2 square root of 3 divided by negative 2 plus 4 divided by negative 2. This is going to give us negative square root of 3 minus 2. Now, you may have the question in your mind, do I really have to rationalize the denominator? Is it necessary? Well, let's compare the two answers. Which one do you think is simpler? This original answer that we came up with that contained the radical in the denominator, or our rationalized form? You'd have to agree this one is simpler, the rationalized form. It's not in terms of a fraction, and it's got a lot fewer terms. So one of the purposes of mathematics is to express everything as simply and efficiently with as few terms and signs as possible. So rationalizing the denominator certainly makes an improvement on this problem. Now, let's be sure about our answer by checking with our calculator. We do have an exact value, but we can certainly verify this with our calculator. The original problem was in radians, so after a quick check, I can see that I'm in radian mode. So I'm going to evaluate the original problem. That is tangent of 7 pi over 12. The calculator gives a decimal approximation. If we type in what we came up with, that was negative square root of 3 minus 2, we can see we get the same decimal approximation. So we can have confidence that our exact value is correct. All right, let's try tangent of 15 degrees. Now on the previous problem, we were able to use our tangent of a sum formula. This one we can express as a difference between two common angles on the unit circle. That is tangent of 45 degrees minus 30 degrees. Remember, don't just use random angles, use unit circle angles, or common angles on the unit circle. Expanding this with our tangent of a difference formula, we'll have tangent of 45 degrees, keep the same sign from the argument here. That's going to give us minus tangent of the second angle 30 degrees. Then in the bottom, we'll have 1 plus, I'm switching the sign, the product of those two tangents. That's tangent of 45, tangent of 30 degrees. Now, let's go ahead and evaluate those tangents. Tangent of 45 is 1, and tangent of 30 degrees, let's think about y divided by x at 30 degrees on our unit circle. We're going to end up with 1/2 over the square root of 3 over 2. And when we simplify and rationalize, we'll get square root of 3 over 3. In the bottom, the good news is we've done the hard work to evaluate the tangents, so we're going to see them repeat here. Tangent of 45 is 1, so I'm not going to write that down. Tangent of 30 degrees is square root of 3 over 3. Now, we have two algebraic problems here. One is that we have a complex fraction. That means more than 2 levels in our fraction, and we have a radical in the denominator. So I'm going to take care of each one of those things one at a time. Let's start by multiplying the top and the bottom by 3 in order to take care of our complex fraction problem. So I'm going to distribute the 3 to each term in the numerator, and I'm going to distribute the 3 to each term in the denominator. That will give us 3 minus, notice the denominator cancels on that second term, 3 minus the square root of 3 over 3 plus the square root of 3. Our next problem is now to rationalize the denominator. So let's multiply by the conjugate of the denominator, 3 minus the square root of 3 times 3 minus the square root of 3. Remember, keep the same two terms and change the sign in between. Now, we've got quite a bit of FOIL to carry out. So starting with the FOIL in the numerator, 3 times 3 gives us 9. The outside and inside terms are both 3 square root of 3. Negative 3 square root of 3. So when we combine those, we'll get negative 6 square root of 3. And for our last terms, negative square root of 3 times negative square root of 3 is positive 3. In the denominator, working with our conjugates, the product of our first two terms is 9. The outside and inside terms cancel, and the last have a product of minus 3. Simplifying in the top by combining like terms, we have 12 minus 6 square root of 3. And in the bottom, 9 minus 3 gives us 6. Now, let me show you kind of an alternative approach. Over here, we split up the fraction, so that's one way to do it. Another way is to simply factor out your greatest common factor. So if I factor out a 6, that's going to leave behind 2 minus the square root of 3 divided by 6. Then, because you're dealing with factors, you can go ahead and cancel those 6's. So our final answer looks like 2 minus square root of 3. But let's be absolutely sure. Let's evaluate this on our calculator. So in degree mode, let's double check. Yep, in degree mode, we'll evaluate the original problem, tangent of 15, and we'll type in our result, 2 minus the square root of 3, and looks like we did a good job. So we can be confident that we came up with the correct exact value of tangent of 15. Now remember, it is essential to both rationalize and simplify your complex fraction, because in both of those moves, you can see we've really simplified the answer. All right, let's finish out this section with a couple of identity problems. In example 5, we want to, we're going to simplify first. Not ready to verify the identity yet. Simplify each expression. So example 5, notice the pattern. We have the sum of two tangents in the top and 1 minus the product of those same two tangents in the bottom. The angles match in the top and the bottom, and I can see I have a plus here and a minus here. So this is going to be tangent of a sum identity. That is tangent of pi over 9 plus pi over 6. We can go ahead and get a common denominator of 18 for each of those fractions. Notice if we multiply 9 by 2, we'll get 18, so I need to multiply the numerator by 2. For a common denominator of 18 here, we multiplied 6 by 3. Multiplying the top by 3, we're going to get a 3 pi over 18 there. Thus, we end up with tangent of 5 pi over 18. And that's definitely simpler than the original expression. For example B, notice we have a cotangent here and here, and we're going to have to simplify those or replace them with tangents in order to use our new identities. Cotangent of pi over 2 minus pi over 3, notice that's a cofunction identity. We could replace that with tangent of pi over 3. So we can do that in the top. Second, notice we have a tangent of negative pi over 6. Well, because tangent is odd, we could rewrite that as negative tangent of pi over 6. Working in the denominator here, we have 1 plus tangent of pi over 3, and cotangent of pi over 2 minus pi over 6 can be replaced with the the cofunction, tangent of pi over 6. Now, notice our angles match. We have the difference of two tangents in the top and 1 plus the product of those two tangents in the bottom. So we can recognize this is tangent of a difference. That is tangent of pi over 3 minus pi over 6. If we get a common denominator there, we have tangent of 2 pi over 6 minus pi over 6, and that simplifies to give us tangent of pi over 6. On the unit circle, we can go ahead and evaluate that. At 30 degrees or pi over 6, the value of tangent is square root of 3 over 3. One last problem. Here's where we're going to verify the identity. So we have cosine of alpha plus beta divided by sine of alpha plus beta. And on the right, we have 1 minus tangent alpha tangent beta divided by tangent alpha minus tangent beta. I'll begin by copying down the left side exactly as it appears. Cosine of alpha plus beta divided by sine of alpha minus beta. Then we'll show step by step that it can be translated into the expression on the right side. We have the opportunity here to apply both our cosine of a sum identity and our sine of a difference identity. Cosine of alpha plus beta can be expanded as cosine of alpha times cosine of beta. Change the sign sine of alpha, sine of beta. Then in the bottom, we can expand this as sine of alpha, cosine of beta, keep the same sign here, minus cosine of alpha, sine of beta. Now, in order to get this to look like the expression on the right, specifically focusing on this first term, if I want to convert this into a 1, I can divide by cosine alpha, cosine beta. But if I do that to the first term, I'm going to need to carry that out on all 4 terms. So we'll proceed by dividing every single one of those terms by the same thing, cosine alpha, cosine beta. So we have the first term of the numerator divided by cosine of alpha times cosine of beta. Then for our second term, we have sine of alpha times sine of beta. And we'll divide that by cosine of alpha. Same thing, right? Cosine of beta. Now that takes care of our numerator. We're going to divide our 2 terms in the denominator by the exact same factor. That way we're not changing the value of the expression, just the way it's written. So we have sine of alpha, cosine of beta, divided by the same factor, cosine of alpha, cosine of beta. Hang in there, one more to go. We have cosine of alpha, sine of beta, divided by, same thing, cosine of alpha, cosine of beta. Okay, we had to make it look worse temporarily in order to make it look better. But here's the fun part. We can go back and we can cancel like factors wherever possible in all of our terms. So everything cancels out of the first term in the numerator, second term in the numerator, nothing can cancel. We've got the cosine betas out of the first term in the denominator, and the cosine alphas cancel out of the second term in the denominator. When we look at what remains, since everything canceled out of the first term, that's going to leave behind a 1. In our second term, notice we have sine of alpha over cosine of alpha. That can be written as tangent of alpha. Sine of beta over cosine of beta can be written as tangent of beta. In our denominator, we have sine of alpha over cosine of alpha. That's also known as tangent of alpha. And then minus sine of beta over cosine of beta, also known as tangent of beta. So since we have arrived at the expression on the right side, we have verified the identity. So at this point, make sure that you know the formulas for cosine of a sum or difference, sine of a sum or difference, and now also tangent of a sum or difference.